Okay, so we're going to basically pick up on Met Part 2. And I'm just going to share the screen with you guys. So you should now see a screen, my other screen up there with lapse rate on it. So we did cover this last time. I'm running through it again. A, because it's good to go over it several times. B, I didn't record it. And I've added some extra bits into this, which we'll get to. So obviously the basic principle we're looking at is it is a parcel of air that leaves the ground and rises. This parcel of air is basically classified as an adiabatic system. It's an enclosed system, and that's this theoretical parcel of air. So these lapse rates, you'll notice that they're dry adiabatic, saturated adiabatic. It's referring to this parcel of air that's rising. That's the concept this is all based on. So the dry adiabatic lapse rate of 3 degrees C per 1,000 feet it's an actual measurement. It's been taken, it's been calculated, and it works. I think when you get to a certain height, it doesn't work above certain heights, but for our purposes, for reaching the cloud base, it works as a figure. So again, let's go with the basic principles, which is this parcel of air is assumed to be dry. It's assumed to be dry because it hasn't saturated. It's about as complex as that. Once its temperature drops to dew point, the air inside it will form moisture, it will saturate. At that point, it is considered to be saturated. So it has these two states, dry, saturated. And that's the technical side of it. Once it saturates, the cooling rate drops to 1.5 degrees C per 1,000 feet. The environmental lapse rate is 2 degrees per 1,000, but you don't need to know that as much, because you're as you'll see in an example I give later, you're given environmental temperatures at different heights. So the ones you need to worry about are the 3 degrees and the 1.5. So basic principles. So I've basically updated my diagrams to explain what the lines are. So you'll see on each of them, like in this diagram, the blue is the environmental lapse rate. So this blue line would represent actual measurements or predicted measurements at different heights. So it's basically this height, there's a temperature of 19 degrees. At this height, the temperature of about 18, sort of 2,000 feet, the temperature of about 17, etc. So these are temperatures by height. So then we get the basic principle of this, which is a thermal will rise because it is warmer and less dense than the surrounding air. And that's just a basic principle of physics. If you've got a parcel of air, if it's warmer than the surrounding air, it goes up. As soon as it stops being warmer than the surrounding air, it stops rising. That's basically the principle that's involved. Now, it says here, the greater the difference, the faster the rate of ascent. So the difference it's talking about, if you would be, just for argument's sake, if we take these lines that run here from right to left, if they were thermals, then the distance between this line and the blue line is the difference it's talking about. So the wider that gap between your essentially it's the more energy is. Basically, it means there's a bigger temperature difference. If your thermal is at 22 degrees and the surrounding air is 15 degrees, it's going to rise faster because there's that much more temperature difference. That's all that's about. If the gap closes, in other words, if your parcel of air is approaching the temperature of the surrounding air, it will slow down. And that's all that's happening on this thermal effect. Is bigger temperature difference, it will rise faster. Oops, if you want to come in. Sorry, let me let some other bods in. Okay. Hi guys. Sorry, I didn't see you waiting. My apologies. Anyway, we'll carry on. So, yeah, so basically, that's the relevance of lapse rates and temperatures. It's just that basic principle of if the parcel of air is significantly warmer than the local surrounding air, it goes up. It'll go up faster. It's as simple as that. It's one of the reasons why you'll get things like, not that relevant at the moment, but we talk about spring thermals. Is you've got cold air, and then so you can, and the sun heats the ground, so you can get quite a marked temperature difference low down between this parcel of air leaving, and yeah, so it will go up very fast, as opposed to summer, when you'll often get the temperature of the air is generally warmer, and this parcel of air will its temperature difference is not necessarily be that much compared to the environmental temperature. So weirdly, you can get hot sunny days, but quite weak thermals. It's only because of the temperature difference. That's all it's about. And it says any thermal will continue to rise until its temperature is equal to that of the surrounding air. Just the same principle. As soon as it gets the same temperature, it cannot rise anymore. Just basic physics. So here we've just got, again, so the red line on these is our parcel of air, and just sit here. So the red line is the parcel of air. This parcel of air will be cooling at the dry adiabatic lapse rate of 3 degrees per 1,000 feet. So again, this is the blue line is our environmental line. This represents our parcel of air traveling. And these are the notes on the side that relate to each one. So, I mean, these are highly theoretical, and it's rare you'll get this much difference in temperature of a parcel of air leaving the ground. Let's just get real. But it's just an illustration to give you an idea of what happens. So in this first one, if our parcel of air was at 22 degrees, leaves the ground, sorry, 21 degrees. So it will rise, it'll actually hit this first inversion here, which on this diagram is at 500 feet, and it will stop rising at that point. So with a marked low inversion, you'll get what you'd expect, which is, well, per this, you'd have a very strong thermal on low down, petering out really fast. In the same condition, if the trigger temperature was higher at 24 degrees, then you can see that it's going to skip this inversion and hit this second one here, and then before it stops rising. In the third example, if it was at a higher temperature, it would release. It would go up very fast at the beginning, slow down. It would miss this inversion and this inversion to get stopped by the third one. And that's what those diagrams are showing. So this slide is looking at this last example here, and this diagram is simply illustrating like this gap at the bottom is illustrating this gap in the diagram. That's all. So saying, right, at the bottom here we've got from this blue line to this red line. This is an idea of the thermal strength. Again, very theoretical, but the principle is there, which is that the gap between your parcel of air going up and the environmental temperature is how fast it'll go up, which makes sense if you sort of think about it from that point of view. You know, if you've got, if the air is significantly warmer, it will just go up quicker, and that's all it's saying. If we keep it that simple. Okay. So this diagram I've kind of I've explained a bit more in the next three, but bear with me on this one. So any thermal will continue to rise if its temperature is equal to that of the surrounding air. So we've got that basic principle. So on this diagram, what we've got here is our, I didn't label, but so this blue line again is like a snapshot of one of these other ones. So this is our environmental temperature. So it goes up, here it's cooling, and then here we get the inversion at about 4, 5, 4, 6, whatever. This black line is our parcel of air rising. Here is our dew point line. So it rises, dry, 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 gets to here, condenses, saturates. So now we've got cloud base. Now, because it's saturated, its rate of climb, you'll notice instead of going at 3 degrees, now changes to 1.5 degrees. And again, it will now rise, cooling at that rate until it hits the inversion again, and that's your cloud top. So that's just your basic, it's the way the dry and the saturated work together. Now, just to illustrate it a bit more, I'll just go, I've basically taken that similar result and just broken it down step by step. So, and this just splits the elements out, I think makes it a bit clearer. So here we've basically got, this is just a invented set of figures. But here we've got temperature and height plotted on a graph. So, you know, at ground level it's 24, at 1,000 feet it's 17, etc., etc. So this then gives us this line. So this is our environmental lapse rate. These are our temperatures at different heights. And on this particular day, dew point's going to be at 14 degrees centigrade, and dew point has a lapse rate of 0.5 degree centigrade per 1,000 feet. So for every 1,000 feet you get up, it's changing at that rate. The dry adiabatic is 3 degrees and saturated 1.5. So if we now add on our, so this blue line is now our dew point line. It shows dew point as it cools and as it gets higher. The red dotted line is our parcel of air. And more realistically, you get this phenomenon where the parcel of air actually leaves the ground at pretty much ground temperature. It rarely leaves the ground at sort of 10 degrees more than ground temperature. So what we now see is probably something a bit more typical of a thermal here, which is if you look at the gaps, it's actually starting off weak, and it actually builds as you get higher. So now we've got here on the dotted line is our thermal rising and cooling, and it will keep cooling until its temperature drops to dew point. Okay, and there we go. Final one. So having reached dew point here, that will be our cloud base, which in this case is 4,000 feet. So now instead of rising at cooling at this rate, it now cools at 1.5, and it will now meet the inversion at about 6, 7, under 7,000 feet. So this point here will be cloud base. This point here will be the top of the cloud. Okay. So I think I was just trying to simplify it, break it down, and separate those, just make it, I think, a bit more obvious. And this principle here gives you this basic sort of rule of thumb, which is that you can estimate cloud base by 400 times the difference between the forecast, the ground temperature that something will release at, and dew point temperature. It's just based on this calculation of, if you've got 3 degrees for dry adiabatic, 0.5 degree for dew point, the parcel is basically cooling towards saturation at a rate of 2.5 degrees per 1,000 feet. That's all that's telling you. But that's just a basic rule of thumb where you can estimate If you happen to know dew point and you happen to know the day temperature, you can estimate cloud base. Okay. So I'm going to, I think, because we've got a bit more time, I will just open up the mics. If anyone's got questions on that section, feel free to ask. If you don't, I'll press on. Okay, cool. So that's kind of a recap of what the last bit, and then the other section we have was this on. This is getting into Tephigrams in more. You do not need to know them in this amount of detail for the exam. Let's be very blunt about that. You just have to have an understanding of what is a tephigram. And a tephigram is simply something that is an analysis, or it's sometimes called a sounding. This gives you a breakdown of the environmental lapse rate, which is, in this case, it's the red line, the dew point measurement, which is this one, the blue line, and the path of a predicted therm. And that's about as much as you need to know from an exam point of view. From understanding it, it's part of the reason I include it is because it's much more realistic than the earlier diagrams for emphasis. So this is very common, what you'll see here in terms of the gap between the dotted line and the red line. So the dotted line is your parcel of air, the red line is the environment, and you'll notice it moves quite close to it. And that's not untypical of UK weather, where when you get in the thermal, it's rare that you're going up at 5 meters per second. That's like unusual. Generally, you'll find sort of lower down, it's tricky, 1 to 2 meters per second. And that means that your parcel of air is only marginally sort of warmer than the surrounding air. So it's going up slower. And then this is what you then get here. So you've got cloud base at this point here. Just above cloud base, you'll see, because the cooling rate changes, you'll see the gap increases. So there is this extra lift as you get to cloud base, and that is sometimes manifest by what we call cloud suck, where as you get towards that, you'll certainly start to find that you accelerate, your rate of climb goes up. Again, this is more, this is not an exam point, this is a flying point. And it is something to be aware of, that as you do get to cloud base, you will often find your best climb starts to occur, usually around about the point where you don't want it, because you're now approaching airspace and you actually have to big ear or spiral or something down out of this climb. Not unusual when you get to about, get high, that you'll get this wonderful lift and you have to come out of it. And it's this phenomena where just above cloud base, it's suddenly kicking off. There's a lot more lift, and it gets stronger. Again, this is just the earlier diagram, but shown on a tephigram, and this is just a zoom in, where you've got your red line, environment temperature. The blue line is the environment dew point. This line I do need to move over at some point, but I haven't. What you kind of have to realize is that the parcel that leaves the ground is leaving the ground with that local dew point. So as it rises, it's ignoring what this environmental dew point is, and it's when its internal temperature drops to that dew point that it condenses. And this will give you moisture and cloud base for thermals leaving the ground. As a small aside, the significance of these two, this gap, is that if there is no gap, like if this red line and blue line meet, then you get basically it becomes completely overcast at that point, because all the air at that point is saturated, and that's where you get this sort of overdevelopment on a day where clouds start off spread out, and then you get to the point where it's just solid cloud. And you'll find if you look at one of these on that day that these two will meet at that point. Okay, that's more of a, it's not an exam point, it's just an understanding of how it works. Right, so then we look, I think, basic covered stability. Air is stable if after being displaced vertically, it returns to its original altitude. So this relates to, basically this relates to an inversion. If we go back to one of these diagrams here. So if we take this point here, the top point between 6,000 and 7,000 feet, if the air tries to rise above that point, it will be cooler than the air temperature, so therefore it can't, so therefore it will come back down. So you'll get this point where it will try and rise because there's this lift, it can't, it cools, it's brought back down again. So that's this definition of stability, which is so it's displaced vertically, it will return to its original altitude. The reason it returns is it's no longer warmer than the surrounding air, so it has to sink, so it comes back down again. And then air is absolutely unstable if the environmental lapse rate is greater than the dry adiabatic. So what does that mean? Let me sort of find. So basically, if we go to here, so what that would basically mean, if you took this red line, and if you imagine that sort of moved over a few degrees to the left, then this dotted line wouldn't meet. Its rate would be that it would basically, this air would then always be warmer than the environment. Because it would always be warmer, it would just, there'd be nothing to stop it, it would just keep rising. And that's the condition you will see on days when there are thunderstorms, is that you'll see a thermal come up on this, and it never actually, it just doesn't reach this line, it just keeps going up. But it will eventually reach it, it'll peter out about 30,000 feet. But so that's complete instability. There's nothing to stop this parcel of air from rising. It's always warmer than the surrounding air. So basic stability is based on that. Is this parcel of air warmer or cooler than the air around it? You have an inversion. The reason it stabilizes, the air rises. It is now, as soon as it goes above it, it's cooler than this air, so it has to sink. And that's basically what's occurring. That. So this, I think we covered these. I don't need to go over this again. These were to do with high pressure, low pressure, and things that characterize them. Just again, the basic data is that high pressure is a subsiding air mass. If air is descending, you have high pressure. Inversions are marked, thermals are suppressed, etc. With low pressure, air is rising, and that's just, as soon as you get that basic concept, pressure systems become fairly easy to understand. And because you've got rising air, along with low pressure, you tend to get this significant convection cloud, mainly because you don't have the inversion stopping the below the point where the dew point occurs. So if we went back to one of these diagrams, so if this was a high pressure day, and if we take this red light environment, if there was an inversion here, before the air can saturate, then you would get no clouds forming, because the air would rise, it would hit the inversion, the the moisture in the air inside would not have dropped to dew point yet, so there'll be no vapor, so there will be no cloud.
Just like today, John. Yeah.
Yes, I didn't spend a lot of time. I was working. I didn't spend looking, but yes. In fact, I can. I could probably bring up today's out of interest. Do you mind if I just divert very quickly? Let me just find today's Tephigram and see if we can just bring it. Let's have a look at a real example. Okay, so if we look at today, just do this quickly, RAS table compact. Today was Thursday, 1 o'clock, and we pull up sounding. Let's grab this one. Ooh, what a lovely day it was. Right, yeah, so if I open this in a new window, okay, so this was today at about 1 o'clock, 2 o'clock British Standard Time. As you can see, if we look down here, very low inversion. It's like got inversion at about what's that, 1,200 feet or no, sorry, about 1,000 feet. And the thermal's not. It's our thermal leaving. It's never going to meet. If we imagine that, like, it would have to rise to about here to get to dew point. It's not going to do it. So it's not getting to dew point. So you have you have no cloud cover. You get a blue skies basically. Yeah, so very much like today. So today would have been.
John,
yes.
Can you please look at the one for Cambridge?
On RAS?
Yeah, for today.
Yeah, sure. Give me a second.
Thanks.
Bring it back up. That close the wrong window. Okay. Right, so RASP compact. Today will take 1 o'clock in lunchtime. Soundings. So you want Buckingham, this one, Cambridge, yeah? So, okay. So here you see much better conditions. I just right. So here we can actually see we've got there we've got a much better thermal activity, and we've got a base here at about probably 3,000 feet. Cloud tops at about 5,000 feet. Very similar to one of the diagrams we've been looking at. We've got a bit this line up here. The black line shows a bit of top cover coming in. There'll be some high cirrus forming. Yeah, so we've got here. This is almost exactly like the diagram we've got. So you'd expect to see clouds forming quite nicely at around around 3,000 feet. Not too bad. Were you in Cambridge? Anyway.
No, I wasn't. It's just it looked nicer.
Yeah.
Is that because it's more inland?
To be honest, I'd have to look at what the pressure was for the day, which we'll take a look at that in a second because we're about to get onto synoptic charts. So I'll leave that there, and then we'll have a look when we get to synoptic. I'll bring the Met up. We'll have a look at the synoptic chart for today, and we'll see how that compares. Okay. So I will come back to that. I'll leave that there and just minimize it. Back to this. All right. So yeah, we'll come up. So I'll come back to that shortly, and we'll recap on that. So the other bit so the last bit was looking at was last time was anabatic, katabatic winds, and sea breeze effect. So probably simpler to go with a diagram. Basically, anabatic winds are winds caused by thermal activity on hills or inland, causing a reduction in pressure. Air then flows from an area of higher pressure to re-establish equilibrium. These winds include sea breezes, valley winds, and thermal winds. So anabatic basically means moving upward, katabatic, moving down. Very simple. An example of an anabatic wind is the sea breeze. That's our most common example. We don't have mountains. And again, I'll just go over it very quickly, which is that it starts off with the sun on the land, heating it, causing the air to rise. Because the air is rising, you now have low pressure. The air will rise. It's got to go somewhere. So, I mean, obviously some will push inland, but more significantly, this bit will push out over the sea, where it cools, descends. You've now got descending air, which creates high pressure. If you have low pressure here and high pressure here, then the wind will move from high to low. So now this generates the sea breeze. And depending on temperature differences, will depend on how strong this is. So you can get, that's why in summer we get very strong sea breezes. We've got the land heating up a lot, creating a relative march over low pressure compared to this high pressure over the colder water. So then that generates and pushes it. In mountains, it's a slightly different effect where during the day you've got the sun heating the valley sides, you've got warm air rising up. So this will give you low pressure at the top. Again, the air's got to circulate somewhere, so it will circulate, and then you get descending air in the middle. You can't just have air going and nothing replacing it. You can't have a vacuum. So the air that pulls the air down. So you then got high pressure in the middle, and you'll get in the bottom. You can get, obviously, depending on the shape of the valley, Venturi and everything, so you can get strong lower down valley winds. I mean, I'm not an experienced mountain flyer, so I can't say I've experienced this. But for those who have, they will tell you, yes, you can be flying quite high in moderate winds, and on the ground it can be howling. It can actually be blowing through at 30, 40 kilometers an hour. And it's one of the things that when you do fly mountains, you need to get very good local briefings on, so you understand the conditions and when it's safe to land and when it's not safe to land. Katabatic means sinking, going down. So katabatic wind is caused by the descent of cool air. Typically, as evening draws in, the upper air level cools and descends. So you can get land breezes where, you'll notice in like summer, end of the day, the wind will switch, and the wind will, you've had sea breeze during the day coming off the sea, and at night time it switches and you get a land breeze blowing out. You can get a land breeze in the morning as well. So basically this, so katabatic, you've got you've got descending air, so you've got higher pressure here, it sinks, you've got lower pressure in the valley, so then it pulls the air down. But again, it's this basic principle: air flows from high pressure to low pressure, and most of this you can work out based on that. So your nighttime or evening katabatic is the opposite, where you've got descending cold air. Now you've got rising air in the middle of the valley, and this is sometimes known as restitutional magic lift, where sometimes you'll see people end of a day right out in the middle of the valley, happily boating about. People launching on the side just being drilled down to the bottom. You don't, let's say I don't know where you get that. Do we have any significant valleys in the UK? It's definitely more to do with mountain climbs. But if you ever experience it, that's the phenomenon. Okay, so that's catches us up to where we were before. The last section on this is to do with weather charts, synoptic charts, so basically the lines on a synoptic chart are called isobars. Iso means equal bars. So an isobar joins points of equal pressure, as we'll see. Weather maps typically show isobars at 4 millibar intervals. A reduction of pressure of 1 millibar is the equivalent to a gain of 30 degrees in height. That's a piece of data I think you need for the exam. It's worth remembering. 1 millibar, 30 feet. So this is like a black and white chart. Which I've got some like pretty color ones in a minute. But basically, yes, you'll see lines on there marked with low pressure and high pressure. I'm actually going to go on to the more colorful ones because they make it a bit clearer. So the following, I will update at some point, but this is from 2018. It was 3 successive days of synoptic charts, just to show what was happening with the weather over those 3 days. And the sort of things you should get used to doing with charts is identify areas of high and low pressure, locate the different fronts, work out approximate wind direction, determine if you have strong or light winds in different areas, decide if you'd expect wet or dry weather and where you would expect it. So that's the data you'll need, to understand it, definitely B for the exam. If you look at the mock exams, you'll see questions of that nature, where you're going to get presented with a synoptic chart and you'll be asked questions about it. So if we take a very quick look at this, you can see, low pressures are marked with an L, high pressures with an H, and the pressure reading for those. So obviously here we can see on this day you've got two cold fronts coming through, one right after the other, chasing this bit of a warm front here. You've got very close isobars, so you can expect from this obviously low pressure, so the air is going counterclockwise around the low pressure system. Close isobars, so here you would expect strong wind. Basically, close to the isobars, the stronger the wind. And you can see the isobars are moving, look at the direction of the isobars. And then remember to get the wind direction at ground level, you take your isobar and just bring it in 30 degrees, to give the ground wind direction. So the upper level wind will be at that. If you remember if I go back to right, so that was the first day. This was the next day, and got again low pressure move. You can see it's definitely dominated by low pressures. High pressure system here, and here you've got an occluded front, but the isobars are spreading out, so the wind is dropping. And then by third day, so now from down here we can see this high pressure system pushing up from the bottom. That's now actually starting to dominate the weather. So you've got clockwise, the air will go clockwise around the high pressure system. So, and we'll move in at sort of 30 degrees. So you've almost got
away at 30 for high.
Sorry, say that once more.
And a high pressure goes away from a high pressure.
Sorry, high. You're absolutely correct. So move out by 30 degrees from the high pressure system. So you would get, if you took that wind direction, add on another 30 degrees, it's probably going to be almost going sort of northwesterly almost. Yeah. So so the isobars are running this way, so the wind would be running roughly about that way at ground level. But you can see this moving in. Like the day before, you've got the high pressure forming down here, but the low pressure still dominates. This then pushes in, so you've now got the wind dropping off, high pressure systems moving in, and that sort of that change in the weather. So that's if we just go back to the actual syllabus briefly. So what you're required to know from Met is this bit here. Fully understand, be able to interpret a synoptic chart to the extent of being able to describe the current weather at selected locations and to forecast likely changes. So for that, you basically need to take your synoptic charts, and what you'll need to do is tie that back to this data on fronts. So you need to look at your chart, see, okay, where's the warm front, where's the cold front, and then you'll know where there's a cold front, you've got these conditions occurring, whereas a warm front, you'll have these conditions occurring. So that will give you, and start, my advice is over a period of days, I mean every day ideally, start looking at synoptic charts, look at the weather, and then actually compare it to the forecast. So if we take a look at, if we just flip to the Met for today, so we continue. Okay, Google. Yes, Google, I will accept your privacy notice because I need to get on with things. Right, no. So if we let's take the coast. Let's take Lewis East Sussex, and so here we've got, so if we look at for tomorrow, we're basically seeing the forecast on, it's per this, sunny in the morning, starting to cloud over, so partially cloudy. We've got light northeasters going east, east southeasterly, going south southeast. So let's now look at the synoptic for tomorrow. So the pressure chart. So that's Thursday. Right, so this is basically Friday, tomorrow lunchtime. And as you can see, very dominated by high pressure. Not a lot happening. So if we just go forward, so you'd expect from this probably fairly light winds, and when it's like this, it can be difficult to predict wind direction. If we just look at today's one for comparison, so with today's one, you've got low pressure. You had the low and the high interacting, so you'd have had here expecting some winds to be blowing through. That's going clockwise and that's going anti-clockwise. Then in the middle of this, you'd have expected these winds to be slightly stronger as a result of that. But by tomorrow, it's the high pressure is dominating. And if we go to Saturday, okay, so Saturday it changes, and we've got low pressure pushing in. We've got a cold front there, the occluded front, broken warm front, quite a mishmash. You won't get anything as messy as this in an exam, I can tell you. If we then look at the forecast for that, go back to Lewis. See what I'm saying. So again, if we check tomorrow, again we can see, like per that, very light winds forecast for tomorrow. You know, anything that's once it gets to like 4-5 miles an hour, it's light. Saturday we see winds picking up a bit. Sunday we're then into much stronger winds. So if we take a look at, if we look at like Sunday, Monday, we can see that strong winds coming through, more overcast. Obviously Sunday morning, some rain. So we could kind of expect to see then, if we go back to the synoptic, we'd expect to see probably a low pressure system coming in, closer isobars, and some fronts coming through. Let's have a quick look and see if that stands good. So we'll go to our surface pressure charts. That's Thursday, it's Friday, Saturday. So here we go. So we're moving into Sunday, and here we see the cold front coming down through the UK. We go to Sunday lunchtime. We've got high pressure here, low pressure here. So between them, we can the UK is kind of, you could expect these generally getting stronger winds being blown down through the UK. And that's if you then go back and look at the forecast, it's reflected in the forecast. And here you've got a front coming through. That's that rain that's hitting the UK. If we have a look at, oops, oh, that's it. Okay, that's as good as we get on the pressure charts. You'd have to, but check them as the days go ahead, and but do that. Compare the synoptic. Take a look at the synoptic. Take a look at the forecasts. Compare the two, and that will give you your understanding of what they're doing. It's the best way of doing it. It's the best way to get familiar with it. In fact, I'll just say, well, let's go back one step. Do to today. Yeah, today did. I mean, you know, high pressure system. The high pressure is. Just looking at the weather over Cambridge. Interesting. I suspect just to be something else happening with the air mass, probably this high and low pressure that caused that better day in that area. That's just a guess. Okay, so split back to this. Right, so what I'm going to do, that's pretty much that's all the data that you need for the syllabus. So what I'm going to do is I'm actually going to stop recording at this point and just take questions. But I don't necessarily want to record all those. So that's the information that people will need. I will now find my button.